Good afternoon, I'm Mr. Ish. Thank you for joining me. Integral test of series. Why is this a very interesting subject for many of us? Because in this video we'll be looking at material that's familiar to us. We'll be now able to use some of our integral techniques to help determine whether a series is convergent or whether it is divergent by means of examination of the integral test. When you're looking at an integral in terms of its integration, you're calculating an area below the curve. But when you're utilizing the integral test, you're utilizing that to help you determine if a series is convergent or divergent. You're not doing any evaluation of this item. You're not evaluating that. The value obtained from a definite integral is not the same as this. Just keep that in mind. For a continuous, decreasing, infinite, and positive series, we have this representation. What are we talking about? A series that is continuous, it's decreasing, and it's infinite, made of positive terms. We have something which looks like this, a function that's evaluated in terms of its sum. You can evaluate the convergence or the divergence by converting it into an improper integral, and you can evaluate that. If the outcome of that improper integral is a finite value, that finite value allows you to utilize the term convergence for your series. If that improper integral appears to be divergent, then your series will of course be divergent. Based on the integral test, if an improper integral outcome is convergent, your series is convergent. If the improper integral outcome is divergent, your series is divergent. We need to examine this by means of two good examples where we work them out fully. But before we do that, examine this particular term right here, continuous. You know what decreasing is. This right here is decreasing. 1 over 2, 1 over 3, 1 over 4, 1 over 5. The value of each of these mathematically is decreasing. You know what infinite is. It's going up to infinity. You know all of that. You know what positive terms are. These are all positive. There's no negative. But what does continuous mean over here with regards to series? Understand that before we go further. 1 over n minus 3, which you know is synonymous to 1 over x minus 3. When you graph this, you know you have a horizontal asymptote, your x-axis, but you also have a vertical asymptote, x equals 3 or n equals 3. You would be looking at some sort of representation over here. So you'd have a function which would look something like this. If you were to do a series evaluation knowing that this right here, vertical asymptote is 3, you can't do the series evaluation from n equals, let's say 2 to n equals infinity, because right in between you have an infinite discontinuity. You must always evaluate for a continuous interval. You can certainly evaluate from n equals 4 up to infinity. There's no break or discontinuity, but you can't involve a discontinuity in your series calculation. You must only look at those intervals which are entirely continuous. So let that be the framework for everything you'll see in this particular video. We're looking at everything here by means of two examples in a general manner, straight to the point. If I were to evaluate this, and you can use the integral test to help you out, you can certainly do so. What would your series look like from 1 up to infinity? You'd have 1 over 5, then you'd have 1 over 7, then you'd have 1 over 9 plus 1 over 11 onwards up to 1 over infinity. It fits everything over here. Continuous, decreasing, infinite, and positive. The question is this series divergent or convergent? Well, think of it in terms of this. You're doing this evaluation 1 over 2x plus 3 dx. You can evaluate it. You can use a u substitution. U is equal to 2x plus 3, and then du is equal to 2 dx, and dx is equal to du over 2. You have u1 and u2 coming into play. Everything with regards to here. You'll have over here u1 is a 5, u2 will be infinity. So suddenly your integral becomes 5 up to infinity. It's an improper type 1 integral, 1 over u du, and then 1 over 2. When you evaluate this, you end up seeing 1 over 2. You have ln u, and then from infinity up to 5. You just do the definite integral procedure. The antiderivative is already determined, upper and lower limit. You're looking at natural log of infinity minus natural log of 5. This right here is infinity. Everything becomes infinity in terms of your improper integral outcome. Everything is divergent. Therefore, this series must be divergent based on this integral test. If the outcome of your improper integral procedure is divergence or divergent, your series will as well be divergent, and you can utilize this to develop that value in terms of a qualitative value. The qualitative values are divergence and convergence, and that's all we're looking at. We're not looking at here at the sum of the series, only whether we have convergence or divergence. This example is a very good example. Let's look at one more. We have this from 0 up to infinity. Notice we don't have 1. 2e to the minus n. You know exponential functions have a domain minus infinity to infinity, so they will generally be continuous and you won't see an infinite discontinuity at play. You will certainly see horizontal asymptotes, but you won't see vertical asymptotes, so this is already a continuous. You're looking at something which looks like 2 over e to the n. But when you open it up in terms of a series, you're looking at 2 over e to the power of 0, which is 2 over 1. But for consistency's sake, why don't I write everything in terms of e? 2 over e to the power of 0. Then the next one is 2 over e to the power of 1. Then 2 over e to the power of 2 plus 2 over e to the power of 3, all the way up to 2 over e to the power of infinity. Notice also this happens to be an infinite series, which we should always be looking at that with regards to the integral test, but it's a geometric series. If you do a common ratio, you'll always have here, just pick any two numbers, one after, one before, and divide them. You'll have 2 over e squared times e over 2. You'll always have 1 over e. My common ratio here is 1 over e. And therefore, you can also determine the sum of this infinite series, and I will do it just because at the end with the improper integral procedure, we're going to do a very useful comparison. The thing you can use here is this, 1 minus r. The first term divided by 1 minus r. Why can I use this? Because I already know it's convergent. It's a series which is convergent because we have a infinite geometric series here at play with a common ratio. Things are progressively getting smaller. I can utilize this. I can get away with this. My first term is a 2, and then I have 1 minus r, 1 over e. I'm looking at 2 over e minus 1 over e. If you simplify all this, you're looking at a 2e over e minus 1. Let's do the numerical value of this. We'll do the denominator first. I have this minus 1. This is my denominator, 1.7182. I'll save it. I have this e times 2 divided by my saved denominator. I have 3.164. The sum of this series here is 3.164. And we'll keep that in mind. An infinite geometric series, which is truly a series here of positive terms. It's decreasing, it's continuous, but we have to see if it's convergent and or if it is not. But we know it's convergent because by means of this we've gotten a good value here. A good finite value in terms of your sum of series is equal to and reminiscent of convergence. But let's look at everything here with regards to the integral test. If you did the integral test, you will look at it in terms of definite integral. You're looking from 0 up to infinity, e to the power of minus n dn. You could have used x here, I'm using n. When you do this, you're looking at 2e to the power of minus n over minus 1. And you know that's the antiderivative of anything which looks like that, from infinity to 0. There's no need for u substitution. You're looking here at minus 2, 1 over e to the n from infinity up to 0. You'll have minus 2. Then you'll do 1 over e to the power of infinity, which is just 1 over infinity, minus 1 over e to the power of 0. What do I get? Minus 2. I have 1 over infinity minus 1. When I'm doing this, this zeroes out. Limit as x or n approaches infinity, this zeroes out. Or any small value divided by infinity is always 0. You have a minus 2 times minus 1. This is equal to positive 2. But what have I done over here? I've shown you two things. By doing this right here, coming at a finite value, I'm showing you that the improper integral is convergent, therefore the series must be convergent. But do not confuse this for this. This value represents here the area below the curve for this improper integral. It should not be the same as this, the sum of series of this infinite geometric series that you see before you. You can use the improper integral test to evaluate the qualitative aspect of convergence and divergence, but do not bring the finite answer as representing that, because it certainly is not. But you've seen here the integral test at play. Again, remember, if the improper integral is convergent, your series is convergent. If the improper integral is divergent, the series is divergent. And why is that the case? Because this series rule is equal to your improper integral function. They're both functions and they're both the same functions. And that's it for this video. Have a good day. Bye.